Alright guys, welcome to part 3 of this tutorial series where we are creating a solution for classifying the digits with the use of Django, Django REST Framework, React.js, and keras. So I would like to begin by apologizing because this part I promised that would be published 1 or 2 days ago. I really couldn't make it on time and I sincerely apologize for the delay. And yeah, the goal for this tutorial will be to create a convolutional neural network, and at the end of the video download the file, which later we will load into our Django project. For all of you that haven't worked with artificial neural networks, I'm planning to create the 5th part as a theory section where we will dig into the details what actually is happening behind the scenes in this part. In the meantime, you can check out 2 great videos by Luis Serrano. The first one is a friendly introduction to deep learning, and the second one is a friendly introduction to convolutional neural networks and image recognition. So the explanation provided by Luis Serrano are simply great. So if you have time, definitely give it a try, because I think this is a great place to start if you are planning to learn about neural networks. And then we have the third link. So by the way, all the links are in the description, and this is just playgroundtensorflow.org, where you can configure your own neural network in the browser. So starting from the problem type, you can select either classification or regression. You can select a data set. You can do all kinds of configuration, and then you just simply need to press play and see what happens. So if you want to understand a little bit more, you can also do some experiments over here. And now we can head over to Google. Please type Google Colab, and we will be using Google Colaboratory Notebook in order to create our convolutional neural network. So I'm just going to press New Notebook, and yeah, just give it a second. One of the biggest advantages of using Google Colaboratory Notebooks is that we can change the runtime to GPU, so we can have access to a free GPU. So what you need to do is to simply, let me just make this a little bit bigger, go to runtime, and here you will have change runtime type, and then you need to select GPU. Okay, so we can now begin from the imports. I'm going to import numpy as np, then we will also need keras, so let's import keras, and let's also not forget about matplotlib pyplot as plt, and we will also need the mnist dataset, and we can get it from keras datasets import mnist. Okay, so shift enter. Let's wait for the connection. All right, so now we can actually load the data, and we will load it into 2 tuples where we will have xtrain. So this is going to be the set of images for training, and next to it we will have ytrain, and then we will have the same for testing. So we will have a test data set of images and labels. X, Y test. Okay. And here we just need to put in mnist load data. All right, shift enter. Okay, so let's check out the shapes of our xtrain and xtest. So I'm going to print xtrain shape, and then I'm going to copy this and put it over here, xtest shape, and shift enter. And here we have 60,000 of samples of images, and here we have the dimensions of the images. So it's 28 by 28 pixels. And regarding the test, we have 10,000 samples and also 28 by 28. So let's check out the shapes of the labels. So instead of putting xtrain, I'm going to put in ytrain, and over here ytest. Shift enter. And as you can see, we have 60,000 of Y-train labels and 10,000 of Y-test labels. So this matches this. Okay, so everything is okay. And let's take a look at one particular record. So I'm going to put in plt em show, and we are going to pass in, for example, xtrain and maybe the first record, first sample, and I'm going to set the cmap to be equal gray. Shift enter. So over here we have 5, and let's check if this is actually true. So I'm going to simply go to ytrain and pick up the first label. Shift enter, and we have 5. So everything is all right over here, but the problem will be when we would like to train our model, because we will need to have a little bit different shape for our data, for the xtrain and the xtest, because if we want to train our model, we need to have 4 dimensions. We need to include the color channels. Okay, so over here we are using 1 color channel, so let's add a 1 after this 28 over here and 28 over here. So xtrain is equal to np expand dims, so we are expanding the dimensions and we want to expand them on the xtrain, and we want to set the axis to be 3. So after the 28, the last 28 that we saw, we are going to add a 1, and then I'm just going to copy this and do the same for the test. So here we will have xtest, and let's press shift enter, and then let's grab those prints from over here and copy them below. And I got the wrong one, sorry. It should be, of course, xtrain and xtest. And now, as you can see, we have an additional information about the color channels. So we can proceed, and the next part will be regarding one-hot encoding. So we do this simply for our model to perform better. We will see the difference soon. So over here we have a record before one-hot encoding, and now we can do an import from keras utils and then np utils. We want to import to categorical. And now we can simply write down ytrain is equal to categorical, and we want to pass in ytrain and put in 10, because we have labels, we have digits from 0 to 9, so altogether we have 10. And the same we will do for the y-test. Y-test, y-test. Okay, so let me press shift enter, and now let's do the same thing over here. So I'm just going to copy ytrain and put it below, and let's see what we get over here. We get an array with data type float 32, and we have 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. So over here we have 5, and here we have 1, which is a representation of the 5. So here we have 0, 1, 2, 3, 4, 5. Okay, if here we would have 7, it would be 0, 1, 2, 3, 4, 5, 6, 7, and the 1 would be in this place. Okay, 8 would be in this place, 9 would be in this place. So this is how it works. So the next step will be to normalize our data. We do this because we want to have the data in the range between 0 and 1, and since we have a pixel color intensity from 0 to 255, it's better for the performance to have the data normalized. Usually what happens when the range of values is too big is that higher values dominate over the lower ones, making them simply less valuable for the neural network. So we can do it very easily. We just need to put in x train and then x test, and then set this to be x train divided by 255 and x test divided by 255. And now we have our data normalized. Now we can simply create different models and run them on validation set. We haven't covered this topic just yet, but we should right now experiment a little bit, create different models, and the one with the smallest error will be the one that we should keep. And on this model, we would do testing. So we would use the test data set, okay, on the best model. But for our case, we are just going to create one model and simply save it and download it. So again, we will need to do some imports from keras models. We want to import, first of all, the sequential model. Then let's grab some layers for our network. So we will have dense. You also need a dropout layer. We'll talk about this shortly in just a second. And also flatten. Okay, then let's also take in optimizer. We will be using Atom. So from keras optimizers, we want to import Atom. And also we'll need to have some layers for the convolutional neural network. So from keras layers, we want to go to convolutional, and from here we want to import max pooling 2D and conv 2D. All right, so below we can create a function which I'll name my conv net, and I'm going to add one in case if you would like to experiment a little bit later and create other models. So here you could put in 2, 3, 4, and so on. But I'm just going to create this one, but the name of the function will be myconvnet1. And we can begin by writing model is equal to sequential. We will be using a sequential model for this. And right now we need to add convolutional layers that consist of filters in order to recognize features of images. So I'm going to write down model add, and we are going to use the conv2d, and we will be using at first 32 filters, and then we will have the kernel size 5 by 5, and we need to also specify the input shape over here. So it will be 28 by 28 and one color channel, and we will also have activation function set to relu. So for now, what you should keep in mind regarding activation functions is that they introduce nonlinearity to the neural networks. Okay, so we have this set up, and this is our first layer. Now what we need to do is to scale down each feature map. We have 32 because we used 32 filters. And yeah, we want to scale it down to half its size by applying 2 by 2 max pooling layer. So we can write down model add max pooling 2D, and here we just need to put in 2 by 2. Max pooling 2 by 2. And I missed a parenthesis over here. Max pooling 2 by 2. Okay, now everything is okay. And yeah, let's repeat this, but this time we will have a different filter size. We will be using, instead of 32, 16 filters, and here we will have a kernel size of 3 by 3. We don't need to specify the input shape anymore. And we will also have this activation function set to relu, and here with the max pooling 2D, nothing will change. Next, we need to use the flatten layer in order to pass the data through the fully connected layers. So let's put in model, add flatten, and over here we don't need to pass anything. And let's add a dense layer, which is basically a fully connected layer. Let's put in 100 units, and we would like to specify the activation function to relu. So activation, and let's put in relu. Okay, so right now what we would like to do is to also add a dropout layer. Adding dropout layer basically means that randomly we will turn off neurons, and this is done to prevent overfitting. We will talk about this shortly in just a second. So I'm just going to put in model add dropout, and I'm going to pass in 0.5, which basically means 50%. And then we will add another dense layer, model add dense. This time I'm going to put in 10 units, and the activation will be set to softmax. Okay, and why softmax? Because softmax activation function allows us to do classification with probabilities. So for example, we have a car, train, and an airplane, and we are passing one of those images through the neural network, and at the end we get some probabilities that the image that we passed in, which is actually, let's say, a plane, is in 70%, we are 70% certain that this is the plane. Then we are 20% certain that this is a train, and 10% we are certain that this is a car. Okay, so this is basically how this is working, and it's very often added this activations softmax at the very end, because the next step is to compile our model, and here we also need to talk about some definitions, starting with a loss function, which is also known as a cost function or an error function, and this is just a way of evaluating on how our model performs. We simply compare the predictions with the actual outputs, and based on that the error is calculated. The bigger mistakes we make, the bigger the error. Okay, so as the next step, we backpropagate this error and update the weights in order to do better the next time in the next iteration and simply minimize the error. This is based on gradient descent. This is a very important topic in machine learning and neural networks. We will go a little bit more into the details on this bonus theory section. Okay, then we have an optimizer, which in simple words will help us to achieve our goal, which in this case is to minimize the cost function, okay, by finding the optimized values for our weights. We will be using the Atom optimizer for this. Inside we need to specify the learning rate, which is nothing else but some kind of a step size at each iteration when we are moving towards the minimum of our cost function. So here we have to be careful, because if the learning rate is too small, it will take longer to train our neural network, but if it's too big, we can overshoot the ideal state. This is again based on the concept of gradient descent, and again we will talk about this in this theory section. Okay, so right now what we can do is to write down model compile, and we will be using this Atom optimizer, and here we will specify the learning rate to 0.01, and because we are dealing with hot encoded labels, we need to use categorical cross entropy. Okay, and also let's add matrix, this additional matrix accuracy. All right, so finally what we need to do is to simply return model. Okay, so let's press Shift Enter, and here we have some error input shape. Okay, so I forgot about the comma over here. Shift enter again, and now everything is okay. So now we can instantiate our model. I'm going to set a model variable and assign it to my convnet1. Okay, so let's press shift enter again, and now we can write down model summary, and here we will have some information about the layers, the output shape, and the parameters. We won't go into details just yet. We will talk about this more in the theory section, but right now it's finally time to train our model. And yeah, we use the training for the model to learn the standard parameters, which are weights and biases. And here we need to, again, discuss a few topics, beginning maybe from the epochs. And the epoch is a hyperparameter that basically indicates how many times we will pass the entire data set through the neural network. So in our case, how many times we will pass 60,000 samples through the neural network. Once we are talking about epochs, we also need to discuss batch size. We will use mini batch in order to pass the data through the neural network in small batches. Then the error will be calculated with the use of backpropagation. Weights will be adjusted, and then we will run simply the next iteration, hoping to get better results. So how to get the number of iterations per epoch? We get this by dividing the number of samples. So for example, let's say we have 10,000 of samples by the batch size. And let's say that we set the batch size to 100. That means that we need to divide 10,000 of samples by batch size equal to 100. And this will give us 100 iterations per epoch. While training our model, we also use the validation set. So we talked about this before, and we are going to create the validation set based off our training data in the next line of code that we are going to write. So we are going to set up the number of epochs, we are going to set the batch size, and then we are also going to create the validation set. But what's important about this validation set is that it's used to fine-tune the hyperparameters. We already know that number of epochs is a hyperparameter, but also we have, for example, learning rate, the number of layers and units, the batch size is a hyperparameter, activation functions, and so on. The thing is that complicated and complex models simply tend to overfit. We work on the validation set to set up the hyperparameters in different configurations to simply reduce the complexity of the model and prevent it from overfitting. But then again, what is overfitting? And again, we will talk about this in greater details in the theory section, but this happens when the model learns the training data too well, but then it doesn't generalize well from the training data to the unseen data. And I don't know if this is a good example or not, but back in high school, I simply hated biology and I often didn't study for the tests. Instead, I learned the questions from the previous years. So I got some questions from older colleagues and I simply learned them, okay? And if the questions were the same, I was able to get a good grade writing definitions I even didn't understand. And if the questions were completely different or slightly different, I simply failed. And if I would use that time to get some general knowledge about the topics on the test, I would most of the times do a better job. And I'll give better and more proper examples in the theory section. Right now, let's work finally on writing code for the training. So I'm going to create a variable over here called history. And this is going to be model fit. And here we need to pass in, first of all, the X train and the Y train. And then we need to put in the information about the epochs. So we will be using 8 epochs. And also let's create our validation data. and I'm going to put in 0, 2. So 20% of our training data will be considered over here as validation data. And also, let's not forget about the batch size. So in this case, I'm going to put in 256, not 156. And I'm going to put in verbose is equal to 1 because we want to see the progress below. And let's also shuffle. Shuffle, let's set to true. All right. So we have 8 epochs with the batch size of 256. I calculated that 20% of the training data will be moved to the validation set. That gives us 60,000 samples times 20%. That means we will have 48,000 samples in the training data and 12,000 in the validation data. And this should give us a result in terms of iteration of 188 because we have 48,000 of samples in our training data and we set the batch size to 256. 48,000 divided by 256 is 187 and a half, and we round this up to 188. And again, verbose is equal to 1. We just simply set it up because we want to see the progress below, and then shuffle is equal to true because we simply, as the name suggests, we want to shuffle the data and then create the batches, okay? So yeah, it's finally time to do this. So I'm going to press Shift Enter, and here we have our first epoch. And here we have the iterations. So as you can see, 188 is here we have the epochs, and within each epoch we are having 188 iterations, and we are simply passing with each iteration 256 samples. Here we have the loss, the accuracy, the validation loss, and the validation accuracy. So to see this in a better form, let's do some plotting. I'm going to put in plt plot, and let's take a look at first on the loss and validation loss. So I'm just going to put in history.history, grab the loss, and then I'm going to copy this, paste it below, and here I'm going to change the loss to validation loss, okay? And then I'm going to set the title. PLT title will be loss, and we can also add a legend, so PLT legend, and let's put in training and validation, okay? And then PLT show. So let's see, what do we get here. Here is how the loss is going on each epoch that we wrote, okay? Because here is actually the value of our loss, and here are the epochs that we were performing. And let's do the same one for the accuracy, okay? So I'm just going to copy this and paste it over here, and let's put in accuracy, and then validation accuracy, and change the title to accuracy, and here we will have, okay, I made some mistakes, training. I hope this is the correct way to spell it. I'm not going to worry about this right now. Just going to copy it, paste it. So we have training and validation accuracy, and let's press Shift Enter. And here is how the accuracy is represented. How does it progress on each epoch that we made? And we will discuss this a little bit later in the theory section. But for now, what's very important is to finally evaluate our model, because we have a trained model and it's accepted by us. So now we can use the test data for the final evaluation. Usually only the best model will be able to see and work on the test data. Okay, so over here what we can do is to create another variable called score, and this is going to be model evaluate, and here we need to pass in simply the x test and the y test, and this time we will set the verbose to 0. Okay, let's press shift enter and let's see what is the actual score. So I'm going to put in print and then error, and this will be score 0, and I'm going to copy this, paste it below, and here we will have the accuracy, and this is going to be score 1. All right, so let's see. Okay, so we have almost 99%, and this is absolutely acceptable. And the final step is to save the model and then download it. So I'm just going to put in model save, and here I'm just going to write down maybe CNN. So here we just pick up a name. How do we want to save it? CNN model, and we need to put in H5 format. So let's press shift enter, and finally let's download the file. So from Google Colab, we want to import files, and now we can simply write files download, and we want to download the one that we saved over here. So I'm just going to grab this, copy, paste, and shift enter. And as you can see, we are downloading our model, and save this model because we will be using it in the next part. And that's it from me today. This was probably the most difficult video that I recorded so far because, you know, my English isn't perfect. I'm doing my best to speak in a way that you can understand me. But sometimes, you know, you forget some words, sometimes you pronounce them wrong, sometimes even you say the wrong words. So I didn't have also the graphics to back me up. I just ordered them. So probably within 2-3 weeks I should get them, and then I can start working on part 5. Anyway, I hope with the use of the videos in the description you will be able to understand what is going on, and also, you know, just don't lose the file. And we can do one more thing. Actually, we can change the title over here to, for example, my CNN. So if you would lose the file, you can always log into Google Colaboratory, select this my CNN file, run the cells again, and then download this model, and yeah, have it for the part 4 where we will use it, where it will be absolutely mandatory. Okay, so I just want to say thanks for watching, have a great day, and hope to see you in the next one. Take care and bye bye.